My name's Joel Hom. I'm a senior engineer at Contech Engineered Solutions. My role there is working with owners, contractors, and engineers to develop buried bridge structures, primarily using galvanized steel in a variety of applications, from large DOT structures to small culvert projects and everything in between. So my role is really kind of integrating with manufacturing and design and in the field to find the best solutions and find all the innovations that I can on the projects we do. So what I'm talking about today in this webinar is going to be focusing on galvanized steel buried bridges and some of the different types of designs and applications that we're using it for, which are really made possible through the galvanizing, through the use of galvanizing. So the first one I'm going to talk about is a project that we did recently out in Washington State near the Seattle Tacoma Airport. This was the extension of Veterans Drive through tunnels that were built below I-5 without doing any sorts of detours or taking any of the lanes out of service. This project is located just south of the airport. This is I-5 running north-south, and Veterans Drive comes in from the east here. And the project involved extending that through underneath I-5 to get access to the other side. This was done through design build, which is really the only way these types of projects can happen. There was a lot of coordination with the contractor and the engineering team to look at all phases of the project to make sure it was going to work. This was I-5 in that area has 10 lanes of traffic, and they were all to be left open during construction. There were two structures that were installed there, one eastbound and one westbound. And this was built through phased construction, which is how we were able to keep the interstate in service the whole time. Washington State requires special seismic racking analysis to assess potential for seismic loading. Um, these flexible buried structures are uniquely qualified or able to handle those types of loads because they are flexible. So it's becoming a more and more common use in seismic areas for that reason. And then because of the lengths of these structures, the DOT wanted to do some sort of a structural fire analysis, which was really unique aspect of this project where we were able to do some innovations. This is just zooming in a little bit more, showing Veterans Drive from the side here, and then these structures are roughly where the red lines are there to get access to the other side of the road. The structures were about 190 feet long each, which was really what was driving the need for the fire engineering analysis. With the lengths of those tunnels, they wanted to evaluate what would happen to these structures if there was a vehicle fire, and just in terms of understanding the behavior, and then also to help them to design a 1IR rating of fire protection system. So we engaged a consultant, Simpson, Gupperts and Hager, to help with that analysis. They did 3D finite element analysis just to establish the fire, the temperature that the DOT had specified, and share the results on the performance of the structure, so they could hand off to a fire engineering company to determine what type of protection system they wanted to use. There was a report that was done around this analysis, presented at the Transportation Research Board annual meeting several years ago. That's a whole separate topic that could be its own webinar. And if anyone wants more information, I'm happy to share that if you reach out to me. So our primary role in this project was to help develop the solution, address how the phase construction would work, and then to collaborate with the design team throughout the whole process. So as we're developing the solution, these types of structures will typically, what works best would be a custom geometry. So in order to do that, what we start with is basically what are the rules for the site? How big does the structure need to be, and how much room do I have to fit it in? So the engineer provided some pretty rigid requirements as far as the inside clearances for eastbound and westbound traffic. One of these is wider than the other because there's a pedestrian walkway included with it. And then you can see they have different elevations for the road clearances. And then there's this fixed distance of 10 feet in between them. So that sort of established the rules for what the structures had to go around. And then we had limitations for the road elevations inside, as well as the elevation for I-5 over the top, and then minimum clearance requirements to achieve. So with all of that information, we can pretty easily customize a specific shape that will fit in that application. And then from there, we start going into the engineering analysis to design the thickness of the material and other aspects around the design. This often ends up being somewhat iterative as we're working through it. We'll present something to the design and construction team, and they come back with comments, and then in the end, we end up with what's shown here is what we use for this project. This was constructed, as I mentioned before, they had to keep I-5 open during the whole time, 10 lanes of traffic. So this was constructed in 4 stages. The first stage was they provided some temporary traffic lanes off to the outside, and they excavated in the median and built some temporary soil nail walls. And then after that was done, we placed the footings and assembled the structure. The next phase, built the structure, and then using temporary MSE walls on both ends of it, mechanically stabilized earth walls, because they could be built vertical and to limit the footprint of the structure. Then the traffic is moved on to this section, and then excavation continued to, I believe that's the east end of the structure. So we excavate that out, build out the footings, and then keep assembling the structure. Each ring of this structure is about 2.5 feet wide. So it's pretty easy just to keep continuing on with assembly. So that when that's completed, then they have the final permanent MSE wall on that end of the structure. So that end of the structure is basically done. Shift the traffic over, then do the same thing going in the other direction. So the third stage 3A here involved another temporary soil nail wall. They couldn't quite excavate all the way out. So build that, put traffic on it, and then finish excavating, and then you put the permanent wall on the other end of the structure. So this is kind of a closer up view of some of the assembly process. This is one of the temporary soil nail walls in the background here. These structures both consisted of rings of 5 plates in each ring. That was 2.5 feet wide. So they're assembled often, sometimes plate by plate, or sometimes you can pre-assemble the whole ring and attach it at once. That's really kind of up to the preference and capabilities of each contractor. There are lots of ways to do it. Another view of that same stage, you can see both of the temporary walls here. They're working on the assembly on the structure in the foreground here. Another view as they're finishing up, you can see some of the individual plates kind of being staged in the excavation here. So this actually goes fairly quickly. Most contractors can assemble with this type of a geometry around 30 to 50 plates per day, which is a pretty good rate. Then after that was done, they backfill it, put your temporary wall on there, and then continue with the excavation. Another view from the inside of the structure. So these are medium-sized structures, I would say. That I think in the 35 or in the 40-foot span range. The large structures will usually be like 50 to 60 feet in span or more. This is as they're coming up to the end of it. You can see the face of the temporary MSE wall here. We always make sure the structure sticks out about 3 to 5 feet or so it allows some flexibility for attaching it as you continue. So in this image, they're in the process of excavating, and then they're going to finish out the foundations and complete the assembly. So this is the end of the finished structure here. They're just gonna add it on, and they remove this wood here and backfill out, and then this is the permanent precast panel faced MSE wall on the end. On this project, they had a webcam for much of it, so we were able to capture some of the different how the phasing worked here. Um, so it's phase one, and then they're getting the pavement placed over the top, then starting the excavation on the east end there, and then the same thing starting where they finish the first phase and just keep building it on out. And there they are, pretty close to the end there after the pavement was placed. So this is what it looks like now. This was taken a few months ago. Pretty clean look. You can see on the inside, you don't see the corrugations, and that's because on this one, we thought they were going to use some sort of an intumescent fireproofing, since that could be applied essentially like a paint onto the inside of the structure. They opted to go with this fireproof panel system that attached on the inside. This next project is in Minnesota. This is a ALP replacement on a couple of locations on a creek that had frequent flooding and road damage issues. One structure was a 30-foot, 10-inch span box structure, and then another crossing had a 26-foot span low profile arch. Two different crossings of the same creek relatively close to each other. This project is located near Finland, Minnesota, which is about halfway between Duluth and the Canadian border on the north side of Lake Superior. Breezy Point Lane consisted of replacing 3 culverts. At this site, they couldn't change the road grade, so this is similar to the SR 509 project, where they provided some minimum requirements for the structure size. We of course they wanted to improve the flow and provide for fish passage in this area. So the structure we installed there was much larger than the 3 6-foot diameter culverts that they had. And then they wanted to extend the footings deep enough to be below frost depth, which allowed us to use, and because of the site conditions, allowed us to use galvanized steel footings for this project as well. This is a before video. So you can't see all three culverts here, but they're kind of hidden. This is during the spring thaw in May, before the structure was built. Um, as they're kind of walking around here, you can see that this is a frequent occurrence in this area in the springtime. These culverts get flooded, and then the road gets inundated, and then you got road damage that you have to deal with every year. This is pretty common in areas prone to a lot of flooding, and also in the northern states in the spring thaw, because the ground's frozen, the water doesn't soak in, and this kind of thing happens. So these are some pictures from during construction, laying out the galvanized steel footings. This is a smaller structure, only 3 plates per ring, but installed basically the same way, plate by plate. And then after this assembly, they came and they filled in riprap kind of along the inside of the structure. This was buried about 4.5 feet or so, so they had a lot of room in here to build the channel. And then this is the same time about a year later, during the same spring thaw. Actually, this was a particularly snowy year, so I think during the spring thaw they even had more flows than the year before. So you can see the stream is flowing through here at a pretty good clip. Lots more capacity and no hint of any kind of flooding on the roadway. So this is just kind of what you would expect any normal stream to be But this is during flood season and no flooding at this location. The other crossing just down the road, a little bit smaller structure. This one had two culverts that it was replacing. It was also skewed with the road, and at this location, they wanted to raise the road grade a little bit. And they actually had some pretty good foundation conditions there. They had bedrock to bear on, so they were able to have some relatively small concrete footings, and ended up deciding to sort of channelize the flow through the footings. Rather than bury the structure in there, they made the footings a little bit taller to handle that. Same conditions basically here. Same stream. These videos were taken on the same day at both locations. Lots of flow here, not as much flooding in this area just because of how the terrain was. So here's some photos during construction. Building their foundation. They basically put a mud sill in there to create an even space over the bedrock after they excavated. Put the footings on top, and then you can see these scalloped edges on the plate are because the structure was skewed. So you're cutting at an angle across the corrugations, and then the engineer designed a concrete head wall to carry those loads to provide the look that they wanted there. Here it is finished with the concrete head wall. You can see the stream flowing through. This has opened up quite a bit more compared to the two culverts that were there before. And then again, an after video, no big deal. You know, it's the spring flooding is not an issue on at this road anymore either. So the last case study here is out east on Garrett County, Maryland. This is right on the West Virginia Maryland border. Really kind of a rural, remote area. This was done in partnership with Trout Unlimited, who was funding the project. And a lot of the goal in a lot of their projects is to restore fish passage and also do it in an environmentally friendly way where you're using a solution that kind of fits in the context of the area, aesthetically and environmentally, and provide all those types of kind of value added improvements. So at this location, we were replacing these culverts here. This Wolf Den Run is basically it's a sort of a mountainous area here in Maryland. It's essentially a drainage area that empties into the Potomac River. So Wolf Den Run goes underneath Shalmar Road. So it's relatively steep, so the water's moving fast. Most of the year it's just a trickle. But one thing that happens in this area as well is when the Potomac River floods and swells its banks, it actually backs up into Wolf Den Run. So that was one of the driving forces behind using a much larger structure here rather than just replacing these culverts. This is a kind of a tough area to drive around in if you've ever been in that area of West Virginia or Maryland. You have a lot of narrow two-lane roads, not a lot of alternative routes. So they needed to maintain access in this area while they were building the structure. They did that by building this shoe fly or this kind of bypass road, which gave them the space to work. They had some limitations too, as far as overhead utilities to work around. Lots of little challenges that kind of added up to what type of structure they were going to build and how it was going to be built. So on this project, we ended up doing a 35-foot span, dual radius arch. It fit in well with the size they need, and aesthetically it provided what they wanted. And in addition to that, we also provided welded wire-faced galvanized steel MSE walls. And that was also something Trout Unlimited was very interested in, because we could do a vegetated version of that to provide some of the context or some of the aesthetics and the value added things on that project. This project had a lot of kind of a rocky area, so they had lot of tough digging, a lot of boulders and things to break up. They put a mud sill in here as well too. They excavated down to to where the footings needed to go, put in a mud sill to provide a level place to build the footings on. This was all built by a contractor crew as well. So they did their own concrete work. They did their own assembly using the things like these backhoes. So that was the heaviest equipment that they had out there. Another 3 plate per ring structure, assembled on their own fairly quickly. After assembly was complete, they proceeded with placing the backfill and building the MSE walls. It was a galvanized steel welded wire face wall, and then the portion that was going to be exposed above grade was going to be vegetated. So they built it with a slight batter and had this special medium kind of be behind the face panels on the wall to promote vegetative growth. And that's what it looked like the spring after this was built. So you're looking towards West Virginia in the background here, and then Potomac River runs on the other side of the structure. And that's it.
Awesome. All right. Thank you, Joel. Appreciate that presentation. All right. Next up, we have Brian Keelerberg. Do you?
Hello, yes,
Oh,
I don't know if you can hear me or not.
sorry.
Yeah,
I cut out for a little bit there.
yeah.
Yeah. Hey, Brian. All right. Next is up is yours. If you can go ahead and share your screen.
I am trying to get it to go. Start broadcast. Yeah, it says 3, 2, 1. You're sharing your screen, is what it's telling me. And now I need to get my
Yep.
presentation up and running. Oops. Yeah, what we're talking about today, again, it's an honor to be asked to speak here. And again, what we're talking about is the Cyclone Bridge or the Buffalo Creek Bridge. And there's a little background that goes on with it. This is what the old bridge was. It was originally constructed in 1928 and then rehabbed in 1956. Now, this is called D22, the road now, but it was US 20 back a number of years ago. And we're faced with issues on piling, and it doesn't. That's some examples of some of the wood piling I've got issues with, but even look at my concrete encased piling, and you'll see the concrete rots off of them. Now, this particular bridge is only located about 3/4 of a mile south of the bridge we're replacing, or maybe closer to a mile. But you'll notice the concrete encasements are rotting off of them. Now, what makes this particularly critical or significant is it was a bridge that I had constructed about 1997. So if I've got to come back in and start doing repairs on a bridge that I built, that means I need to do something different. And you can see how fast that deterioration was going. That was a matter of about 2, 3 years difference in timing between those slides. Yes, you can come back in and do repairs on these things. And that one's a commercial repair there. This is more common what we're doing on repairs. But why don't we build them so we don't have to repair them? And this happens to, I'm pretty sure this picture came out of South Carolina. But you notice they galvanized the part of the piling that's exposed. And there's a whole lot of learning went on in the study. Another thing that's going on is if you start getting your salts underneath your abutments, this was a county just north of me, and you start looking at a piling like that and you start saying there's going to be some challenges on repairing that even. And when I was at the Missouri Bridge Conference just a couple of weeks ago, they're tending to galvanize the ends of their piling too. So this will kind of prevent some of those things from happening. Now, we talked about rehabbing this bridge that was originally built in 1928. Notice the concrete abutments there on the bottom and how the aggregate inside there's actually deteriorating. The concrete's deteriorating on. That was a big part of what we had going on this and why we were trying to address it. And another thing, it's had the Jersey barrier rail on it, which I would regularly get complaints on. That happens to be a pickup coming, but some of the vehicles that you only catch the top of them. So we're trying to put an open barrier rail system in there. But one of the challenges we've got going on is our open barrier rail systems. We end up getting the salts going over the edges, and it's starting to cause some spalling on the edges of the concrete. I've seen some bridges where it has actually destroyed the bridge by the salts doing that. Now, in this particular bridge, we had a construction camera, and you can see mounted up on that utility pole, there's a camera. So that gave us a bunch of pictures to do this. And again, I was trying to figure out a solution to the concrete encasements. And that's why we proceeded the way we did with the designs on this one. You can see we're getting the structure removed. And one of the things we do, this is a 200-foot structure. So what we'll do is we'll have integral abutments, but we'll pre-drill the holes and put a bentonite in there. And that allows the piling to move within the pre-drilled holes. And that's how we're taking care of the expansion contraction. Now you'll notice the coating on this piling, it's a galvanized and coated cardinal red H piling. I'm not an Iowa State graduate, but my assistant is. And so that's kind of where we came up with the name and the colors on this one. Now, this particular year, this was the fall of 2018 that we did this construction. They started at about August, September timeframe, and we had 3 50-year flood events while they're trying to build this 200-foot bridge. Had I followed the standard construction where we'd build cofferdams and encase the piling in concrete, we would not have gotten this bridge built that fall. As it was December 24th when we got it open. Had we not gotten it open that fall, it would have been a complete disaster, and I'll show you some pictures a little later about the problems that were going on with it. As you can see there, the flooding, and there's my cardinal red H piling sticking out of the water. And yeah, the water would recede, and you try and get back in and get to work, then it'd come up again. Like I said, about 3 50-year flood events during this construction time frame. And when the water's up high like this, there's not a whole lot you can do, but kind of just stop back and wait. And yes, this was into October, and they're trying to get things done. Water did go back down, finish the piers. Then we started setting the beams, and the paradigm has changed. Back when a lot of these designs on steel beams came about, they figured materials were expensive and labor was cheap. Well, that's changed in today's world. That's why it's time to change from the simple span, dead load, continuous span, live load designs. Even though it'll use just slightly more material or a little more material, it's still going to be a more economical answer. And you can see them setting the galvanized beams on this project. And so here we are setting that mid span. You can see progress. Here we are decking, and one of the nice things is you don't have to get to the piers. You just deck right on through. You don't have any encasements there at the piers. Yes, winter came in on us too. So this is probably in the October, November timeframe now, which we typically expect snow, and we got it. And then they had to wait till the weather warmed up enough. Now you can do cold weather pouring. What you do is you tarp it off, and then you put salamander heaters underneath there to warm that steel up from the bottom. And I've been in those environments where inside that tarped area with them heaters in there, it becomes nice and warm. Now, why did we galvanize the rebar? And I'm not going to read the whole thing, but it says galvanized steel performs better than epoxy coated, and the difference between epoxy and galvanized increases as the chloride exposure increases. The service life of galvanized decks is 100-year in comparison to epoxy coated decks of 55 years and stainless steel of up over 100 years. So stainless steel is better, yes, but there's significant cost there. And this was a study that was done in Australia. Now here we are placing the concrete, and you'll notice the concrete pump there, pumping the concrete up onto the deck. We're getting complete the deck pour. Yes, we had more snow on the ground again as they're rolling up the blankets and getting ready to take care of the barrier rails. Now, we were talking about the difference in, you see that the black steel versus epoxy and hot dip galvanized and high chromate steel and stainless steel, Galvabar, you kind of see the differences in price. We'll get into that a little bit later, but I'm going to have to fly through for the sake of time. And yes, they've got some case studies in Missouri where they can come in with the steel beams cheaper than you do the concrete slabs. And this particular bridge, we're getting into the economic analysis on it, and it's a new bridge steel girder. It was 1.4 million for a 201-foot bridge that's 40 feet wide. We've been building 40-foot wide. You can see by this that encasing the piers, the galvanizing actually cost me a little bit, but my answer is it didn't cost me anything. It probably saved my career at that time because the spring of 2019 was such horrendous. If this bridge hadn't gotten open and was still closed that spring, it would have been a true disaster because so many of the rock roads were completely impassable from the frost boils. And again, you can see the galvanized rebar cost me about $1.25 a pound compared to the epoxy would have been closer to 85, 90 cents, 92 cents a pound. So you had higher than average costs on that. As it was, it's still about $175 a square foot, which was a little higher than what things were running in that area. The Galvabar was about a 20,000 increase. And you can kind of see how the breakdown, had I gone with the weathering steel beams and the epoxy coated. The barrier rail system I used cost me more too. This was a Wyoming type system, and it's a bolt-on galvanized system, but I didn't want the salts running over the edge of the bridge deck and causing the corrosion on the slabs. And it just seemed like the better answer. So what we did on this bridge got some attention from the Iowa DOT and in particular the Iowa Highway Research Board. And so here in Iowa, it started in 1949. They started taking a half cent off the top of the gas tax to use for highway research to find better ways of doing things. So they came in and they purchased a corrosion chamber. And I'll show you a picture of what the corrosion chamber looks like. 600 days in the corrosion chamber is equal to about 100 years life on this. Now you'll see with the no coating how the weight actually increased, and it'll explain it's a chemical reaction that's causing that. And with the galvanized, it actually decreased the weight. Now that was because they were taking a wire brush and trying to clean it off while they're actually removing some of the galvanizing some of the zinc before it had the patina created. Now, once it creates the patina, then it gets much harder and that loss changes. But you'll see how it didn't gain weight from corrosion like the other methods do. You'll see it painted, and that's a painted and galvanized. And so that paint was actually worked for about 10 years. 10 years of life in the bridge deck's what they figure. So that's about 60 days in the corrosion chamber. And then they started getting some blistering and such on the paint. And there's a lot of differences in types and qualities of paints. And so others may perform a little difference. Then they also wanted to damage some of the paint and see how it worked. And we'll see where they damaged the galvanizing too and see how it healed itself back in the narrower cracks. And again, this was kind of a study going on with Iowa State. So you'll see, this was a presentation from 2022, and they're still kind of monitoring how things are going. Another view of the bridge. This is the interim report that I was actually got a copy of here. And a little bit about the Bridge Engineering Center and everything, but we're going to fly through that for the sake of time and the agreements. And right in their executive summary, they go on to state that concrete encased piling are common for the Iowa DOT and the Iowa County structures and historically have achieved acceptable performance. However, cases of early deterioration and pile corrosion have occurred. As such, interest has grown in using coatings to protect the pilings from atmospheric deterioration. What I saw on this particular bridge, because of the timing and everything, that savings in time far exceeded any of my costs. And now I've still got a structure that lasts over 100 years. According to the ASTM, they go into the corrosion, a little bit about wall corrosion and such, and I'll fly through here, but this gives you the ability, if you want, to get a hold of the presentation and come back and read it. And some of the things I really picked up on here is atmospheric condition causes the corrosion, freshwater corrosion, seawater, which is not applicable to Iowa, and soil corrosion. Now, soil that is in disturbed ground, or steel that is in disturbed ground, corrodes much faster than steel is in non-disturbed ground. In the non-disturbed ground, it uses up the available oxygen and then the corrosion will stop. Well, in the disturbed ground, there's a lot more oxygen available for the corrosion. And so that's kind of what it's saying on top of this here. When undisturbed soils have been found deficient in oxygen and a limited amount of oxygen cannot sustain the corrosion process over time. Now, what's interesting in this picture is you notice they're using helical screw piling, which is some more work that's going on in Iowa. Rather than driving H piling, you would actually use screwed in piling, and that's still research underway. Protective measures such as zinc coatings should be used on pilings where corrosion may be a potential problem at a site. In the case of piles driven through disturbed soils, the protection should be applied in the critical region, which extends from the bottom of the pile down to about 1 meter below the water table, as shown in the previous figure. Going back to what's going on in Missouri, where they're galvanizing part of the piling, so the contracts probably require X feet of piling to be exposed. The contractors are grumbling a little bit because they're having a difficult time figuring out just how many feet of galvanizing they actually have because of the variation in driving the piling. And specifications can be modified to make that work for everybody. Zinc, like other metals corrode, makes a corrosion by produce called patina. This white exterior layer of rust can protect the zinc underneath. The patina layer is created during a series of chemical reactions. And that's what we're referring to either that patina earlier, that patina gets hard and really helps to keep things from corroding in there. And so what they've done is they've got this cyclic corrosion tests in a chamber have been developed in the automotive industry. That was a previous slide. Um, in the automotive industry, they call them CCTs. The chambers developed to run through cycles and simulate the exposure to the steels. And the reading's all in here, but I'm going to skip. Each cycle is a 24-hour period and consists of 3 8-hour stages: ambient stage, humid stage, and dry off stage. Based on NCHRP 20-0, and he's got a question 7, indicated that 150 cycles were equivalent to 25 years. The research team proposed the cycles for this project would be repeated for 600 days to simulate a 100-year pile service life. And that is a picture of the corrosion chamber there at Iowa State University. And so what they did was the salt containing electrolyte, simply called salt solution, was uniformly sprayed on nozzle on the sample. The salt solution was a combination of 3 main salts, including 0.05 grams per liter of sodium chloride, 1.01 grams per liter of calcium chloride and 0.75 grams per liter of sodium bicarbonate. Now, the first sodium chloride and calcium chloride are typically what we're using on a road system. I'm not sure where the sodium bicarbonate came in there. And so what they actually treated was, excuse me, they created the various specimens of bare steel, galvanized steel, painted galvanized steel with paint layer damage, and painted galvanized with both painting and galvanizing layers damaged. And on the damaged part, you see they did 9 total, 3 of them 1/8 inch wide, 3 of them 2/8 inch wide, and a third one, 3 of them with 3/8 inch wide. And you can see the chart up on the top there, what's kind of expected going on too. And here's an example of how things laid out in the corrosion chamber. You can see the bare steel on your right and the painted and the galvanized straight above it. And then the damaged in there too. Now they left the H piling in there. They didn't check it on a monthly basis like they did the samples. So they had little samples too. We're relatively short on time, so I'm kind of going to skip some of this, but they had steel coupon samples, galvanized coupon samples, painted galvanized coupon samples, painted layer damaged coupon samples, and galvanized layer damaged coupon samples. And a little bit more about the 1/8 inch scratch and the 1/4 inch scratch and the 3/8 inch scratch. And you can see how the weight variation, the weight increases as it corrodes. And here's some of the math formulas, which it would be difficult to try and explain. The slope of the dashed line shows the thickness loss per year on one side of the coupon. So that is the theory on things. The plot shows the weight of the samples decreased significantly. This is on the galvanized coupon. And instead of gaining weight, it lost weight. And they're explaining that part of that is because of brush and this with a steel brush, you're actually losing some of that zinc prior to it developing the true patina. Once the patina developed, then they stopped losing weight and it actually started gaining weight. But you don't want it to gain weight because that's the corrosion issues. All of them gain weight as they corrode. And you can see this here's the painted samples here, and here's the damaged samples too. And I'm going to skip on through a bunch on this because of the time factors again. And included images of the corrosion process of the scratched galvanizing. The results showed that a damaged galvanized layer offers better protection to smaller scratches, and galvanized coatings have the ability to restore protection to exposed areas where the scratch with is relatively minor, so that 1/8 inch scratch would heal itself. This is the chart showing the H piling. And if you look on the left with the bare steel, you can see they gained about 4.8% weight. If the scratched, or the steel, excuse me, the galvanized was gaining about 0.8%. The painted was about 0.3%. And the damage was still about 0.2%. And so you can see that they've gained much less weight with the galvanized than otherwise. Here's another chart reflecting that. And the study took advantage of a unique opportunity because we built the bridge prior to them starting to do the study. And so we're going on to some of the work they're doing. Again, you'll see the pictures. The middle slide there is reflective. The guys went out to analyze the bridge and couldn't quite get to the piling. You can see the paint and the different water levels that are showing up at different times. And the economic analysis on this, basically they're saying that the painted and galvanized will easily meet the 100-year lifestyle. They're questioning in cases that maybe go and just heavier H piling. But I look back at the one where the scour was coming under the abutment, and I would be a little nervous about having heavier piling in there and the amount of loss they're getting on that. And kind of flying through with 100, there's again where they're reflecting that. The bridge was opened December 24th, 2018. The frosts of 2019 hit me, the frost boils. That didn't happen to be Buchanan County, but it could have easily been because I had a lot of locations like that where we had to block off the road that became impassable. And here's pictures of what we talk about. The coupons, you can see this is steel. That's where day one, but you can get down to day 600, 100 years later, you can see how the corrosion's impacting that. The galvanized coupon, you can see that too, and you can see 100 years later how it's starting to get to where you're seeing some corrosion on that. And here's the painted and damaged, and you can see day 30, the paint's still working good, or day 60, but after about day 90, that paint's wanting to try and peel. And that's where they figure it gave you another 10 years. Here's what they call the damaged paint on there too. And here's where you're getting into the 1/8 inch scratch. And you can see how they scratched at the beginning, it started to corrode, but it did pretty much kind of heal itself. And here is the 2/8 inch or 1/4 inch. And you can see how it still helped at the end. And here's the 3/8 inch. Now we're getting into the piling samples, and they really didn't take them out monthly and sample them, so it was just the beginning and the end. You can see the galvanized and how it's looking very, very little rust on there at the end at 100 years life. Painted and galvanized. And here's damaged. And there's information is available there. This is not the only galvanized bridge I've done. That's a Nucor's grade 65 steel. This is an Amish sawmill, a press brake tub girder, and that's the Jessup South Bridge. And now we are to the point of any questions, and that completes my presentation.